All right, in part 2 of chapter 7, we're going to start talking about kinetic energy. Kinetic energy is the energy of motion. Now, if you want to know the kinetic energy of an object, all you really need to know, you need to know its mass, you need to know its velocity. If you know its mass and you know its velocity, you know its kinetic energy, because kinetic energy is just 1/2 mv squared. All right? So kinetic energy is one of the types of energy we're looking at and its relationship to work, which is really simple. That if you start off with some kinetic energy v or some velocity v naught, end up with some other velocity v squared, the net work done is simply the difference in the final kinetic energy minus the initial kinetic energy. Or another way to write it is your initial kinetic energy plus any work done on the object gives you your final kinetic energy. We're also going to look at in this chapter the relationship between gravitational potential energy and work. So gravitational potential energy is the potential energy of how high you are, right? If you're sitting on the floor, you really can't do any work falling because you're already as low as you are. But if you, for some reason, were to climb up on top of the desk and then fall off, God forbid you do that, but if you were to climb up on top of the desk and then fall off, on your way down, you could do work. You could do work on anything in your way, right? So gravitational potential energy is another aspect of work, another aspect of energy, and we call potential energy mgh, right? I mean, the potential energy due to gravity is just your mass times the acceleration of gravity times the height you are above the 0 point. It is, in fact, gravitational potential energy that we use to run the old grandfather clocks with the weights that you have to crank up every once in a while. And as the weight slowly comes down, the weight does work on the clock. Right? The weight does work on the clock. So that's another type of energy we're going to be dealing with. All right, and gravitational potential energy, the amount of work you do, whether you lift this straight up or you take up the stairs to get the TV up, you do the same amount of work, right? Because it's just mgh. And yeah, you go up the slope here, right? And you go up the slope there, and you go up the slope there, but you're going a longer distance here using less force, right? That's the point behind inclined planes and stairs, by the way. You're going a longer distance using less force, all right? But in the end, you do the same amount of work carrying the television up the stairs as you do just lifting it straight up with a pulley. Gravitational energy or conservative forces, potential energy, these are all path independent. All right, path independent. So if we launch this car off and it goes up this hill like that, or if we launch it and it goes on this light blue path like that, doesn't matter. The purple path, the light blue path, the fact that the details of in between, all right, are different. When we're talking about conservative forces, the fact that the details in between are different does not impact the final outcome. You get over here, the same amount of work has been done because you've got the same change in potential energy, same change in kinetic energy. All of that all adds up to being the same no matter which path you take. If we look at other conservative forces, potential energy of a spring, and you probably played with springs some in lab. So a potential energy of spring is 1/2 kx squared, where x is simply the distance you've displaced the spring from its rest position, right? So mgh, the h is the distance you've displaced you're an object from its rest position on the ground. For a spring, 1/2 kx squared. For kinetic energy, 1/2 mv squared. Remember, this k is a spring constant. These are all different ways we talk about in terms of objects that are forces and energy that are all conserved, right? If we have non-conservative forces, then we lose energy. Non-conservative forces are things like when we move energy through friction, that actually converts motion into heat energy, right? So friction will change things. Drag force is a non-conservative force. Why? Because no matter which way you move, it always opposes motion, right? Friction. No matter which way you move, it always opposes motion. And it's because these forces always oppose motion, they are non-conservative forces, right? Drag forces slow you down when you're skydiving, but if you were to get on a big spring or a catapult and be thrown up into the air, drag forces would slow you down on your way up too. So the way we write the overall generalized conservation of energy equation is we have our conserved forces: kinetic energy, potential energy, work done by non-conservative forces, and other energy sources, right? And so the other energy sources we just denote as OE. So the ones we'll worry about the most: kinetic energy, potential energy, non-conservative forces like friction, right? We add all these up, we get the final kinetic energy and the final potential energy. Okay, that is it for part 2. When we come back, we'll take a look at the scale of some of these energy sources. All right, talk to you later.